Okay, gentlemen, whoops. I don't know why this is happening, but it is. So that's that. Anyway, so today is March the 19th, and today we are going to do section 10.2, which deals with work. So um, the work is done on a system by external forces. In other words, forces from outside the system. And so um, when a force pushes or pulls on an object, all right, and in this case, we can assume that the wind is pushing on the sail in this direction. And that object moves in a certain direction by an X amount displacement. A couple of things are going on. All right. First, the force is doing work. All right. So that's the important aspect. But as a result, the kinetic energy of the system then increases. All right. And therefore the windsurfer guy dude here speeds up. All right. He goes from a velocity of 0 on the left side of the picture to a velocity of something on the right hand side of the picture. Now, how do I calculate the amount of work that's actually done on the surfer? Well, the formula is very straightforward. As a matter of fact, it's one that you know from last year, and it's shown in the yellow box here on the top of the slide. We've got W equals force times displacement. And essentially what this says in English is that work done by a constant force in the direction of a displacement D, is equal to W. All right. Now, it turns out that although both the force and the displacement variables are vector quantities, work is actually a scalar quantity because the force and the displacement are not always in the same direction. All right, we'll get to that in a few minutes. The unit of work and therefore of energy is what we call a Newton meter, right? That makes sense if you think about it. A force times a displacement is a Newton meter, okay? However, somebody at some point, by convention, somebody decided that we would name the unit of work after Joe Joule, the famous French physicist. And so you can see here on the bottom that 1 joule is equal to 1 Newton per meter. I'm sorry, Newton meter. So that means that if a 1 Newton force pushes an object 1 meter of displacement, you've done 1 joule worth of work. Now, because joule is somebody's name, notice that it is abbreviated with a capital J. Okay, so how do we use this? Well, let's look at this example here. Sarah pushes a heavy crate 3 meters along the floor at a constant speed. She pushes with a constant horizontal force of magnitude 70 newtons. How much work does Sarah do on the crate? Well, all right, so we make ourselves a laundry list, draw ourselves a picture, which we've already done. So we've got a 70 Newton force moving an object 3.0 meters at a constant velocity. And we need to find the value of W. Well, easy peasy. We go back to the previous slide where W equals F times D. And now we can simply use that formula here to calculate the amount of work done. So we begin with the before and after visual overview in figure 10.6. Sarah pushes with a constant force in the direction of the crate's motion, so we can use equation 10.5 to find the work done. The work done by Sarah is W equals F times D. 70 newtons times 3 meters gives us 210 joules of work. All right? And so by pushing on the crate, Sarah increases its kinetic energy, so it makes sense that the work done is positive. Now, what if? Now, I said earlier, what happens if the force is applied to the object in a different direction than the displacement that the object experiences? Well, in that case, then we have to look at the components of the force that are in the same direction as the displacement. So only the component of a force in the direction of displacement does work. we can rewrite this equation then as W equals the parallel force, all right? In other words, the force going in the same direction, or the parallel direction is displacement. Or we can use our knowledge of two-dimensional kinematics and write it as F times D times the cosine of theta, right? Because if this represents the force, then it is this force, or this component of the force, right? Because the dirt bike is moving horizontally. So F parallel is equal to F times the cosine of theta. Therefore, we can write this as F times the cosine of theta D, or as FD cosine of theta. So if the force is at an angle theta to the displacement, the component of the force F that actually does work is F times the cosine of theta. Okay, so with that in mind, let's look at this example here. Let me move myself out of the way. There we go. So a strap inclined upward at a 45-degree angle pulls a suitcase through the airport. The tension in the strap is 20 newtons. Right, tension, of course, is the force in this case. How much work does the tension do if the suitcase is pulled 100 meters at constant speed? All right, so we got a tension of 20 newtons, we got an angle of 45 degrees, and we've got a displacement of 100 meters. And again, we're asked to calculate the value of W. Well, in this case, the figure, shows the visual overview here. Since the suitcase moves at a constant speed, there must be a rolling frictional force acting to the left. We can use the equation 10.6 where the force F equals tension to find that tension does work. W equals T times D times the cosine of theta. Well, the tension is 20 newtons, the displacement is 100 meters, and the theta value is 45 degrees. And if you do the arithmetic here, you end up with 2,000 times the cosine of 45, which is 0.7071, and that gives me approximately 1,400 joules. All right, so the tension is needed to do work on the suitcase, even though the suitcase is traveling at a constant speed to overcome friction. So it makes sense that the work is positive. The work done goes entirely into increasing the thermal energy of the suitcase and the floor. In other words, friction between the wheels and the floor gives us, or produces, heat in this case. All right, now, what happens if you apply a force to an object and it doesn't move? All right, if I push on the wall next to me and it doesn't move, all right, which I hope it doesn't, this is my house, then what goes on here? Right? Well, it turns out that no work is actually being done. No matter how much effort you apply to that wall, it's not going to move, and therefore, no work is being done. So a force does no work on an object if the force A undergoes no the object undergoes no displacement. B, the force is perpendicular to the displacement. In other words, if you push this way and the wall moves that way, no work is done. That's just weird. Or the part of the object on which the force acts undergoes no displacement, even if other parts of the object do move. All right, and so so there's got to be work. In order for there to be work, there has to be a force, there has to be a displacement, but the force and the displacement have to be in the same direction. Okay. That brings us to the end of section 10.2 on work. And for tonight, I'm going to ask you to do homework questions 1 through 6, odd numbers only, which is the 1, 3, and 5. All right. Good luck. God bless. And may the force be with you.